what the title says. So time quasi-periodic, pure gravity water waves in finite depth. This is joint work with Massimiliano Berti from Sissa, Emanuele Haus from Napoli, and Riccardo Montalto from Zurich. Okay, so the talk will speak about water wave equation for in 2D with pure gravity and finite depth, and the result will be the existence of a small amplitude standing wave that are periodic in space and quasi-periodic in time, with symmetry that are even in space and both in space and time, at least the profile, and the result will hold for many but not all values of the depth parameter. I will speak about the difficulties and some idea of the proof. I will begin with the first part to begin with a general presentation of the problem, and then I will give more detail, more technical detail about the proof. So preliminary discussion about standing waves. Probably all of you know perfectly, but in any case it's just like a sort of motivation for studying 2D periodic wave. So consider a 3D progressive wave moving with a fixed profile u with some vector a and the time frequency, which is given by the square root of g and the norm of the vector, and look at what happens when it goes against a vertical wall. We have the interaction between the incident wave and the reflected wave, and at a linear level we can see like this simple formula, cosine of a dot x minus omega t and cosine of b dot x minus omega t. This is at the linear level, and where a and b have the same length. There are two possibilities: or the incidence is oblique, or it is orthogonal to the wall. So the case of oblique incidence was studied first by many authors, two of which are here, at least one, and you can see that in the case of oblique incidence, at the linear level, it is easy to see that there are two, in fact, 3D waves becomes a two-dimensional problem where x1 minus omega t, say, becomes one single real variable, and the problem becomes the linear problem becomes elliptic. Then there is the complication of the nonlinear part, but it is a problem in bifurcation theory that does not contain small divisor because of ellipticity of the linear part. When the incidence is instead orthogonal, this mechanism is not present, and we have so-called standing wave. It means still we have a two-dimensional problem, but this okay, the shape is like the product of two independent cosine, cosine of a dot x and cosine of omega t. This is at the linear level, and it explains why you create a standing wave going up and down if there is an incidence in that way. And this also, still at the linear level, already at the linear level, you can see a small divisor problem because for many, in general, for many values of the parameter omega, you see the spectrum accumulate to zero. This blue eigenvalue minus omega square L square plus g modulus of j are accumulating to zero. Okay, that's like a sort of introduction, and then speak about the problem we studied. So consider the Euler equation that you see many times in these days. So we have a free surface eta and a velocity potential phi on the domain confined between eta and the bottom minus h. We scale amplitude and space so that g, the gravity constant, can be normalized to 1. And we consider the Hamiltonian formulation of the water wave due to Zakharov, which means that the problem can be written as this Hamiltonian equation, where the unknown are the elevation eta, and psi, which is the trace of the velocity potential at the boundary. In this Hamiltonian formulation, the kinetic and the sum of kinetic and potential energy gives the energy, that is the Hamiltonian, and it appears G, which is the Dirichlet-Neumann operator that we see 2 days ago, well explained. It has been studied by many authors. I wrote in green some, but the list is not complete. And it is, as far as we are interested in, the important thing is that G is linear in psi and analytic in eta. It is a non-local operator, self-adjoint, and regarding theory of pseudo-differential operator, it is a pseudo-differential of order 1. And when we are in the periodic one-dimensional setting, it becomes its series in pseudo-differential decreasing operator simplifies a lot, because it is simply the hyperbolic tangent of HD, which is the Dirichlet-Neumann of the flat surface, plus a remainder which contains the dependence on eta, which is of minus infinity order as a differential operator, and when the profile is infinity. This means something you can think at integration by part. It is something acting on the argument C as one derivative, but if you integrate by part, you put the derivative, how many derivatives you want, on eta. This is a simple way to see to say this property. And okay, its definition is the following. We have a profile and a datum C fixed, and we solve the Dirichlet problem on the domain with Dirichlet datum C at the top, and we define G as this formula, which gives the normal derivative of the velocity field phi. So G maps the Dirichlet datum C into the normalized normal derivative, normalized because of this square root of 1 plus eta x square at the boundary. It maps the Dirichlet to the Neumann datum. Okay, this system, Hamiltonian system, becomes this pair of equation in the Hamiltonian formulation, and it is fully nonlinear because there are nonlinear dependence on the higher order derivatives. There are pseudo PDEs and not perfect differential PDEs because of the Dirichlet-Neumann term, and it has a remarkable structure. One is the Hamiltonian structure, so the Hamiltonian is conserved. Also the mass is conserved. I didn't write it, but it is true. And it is also a reversible dynamical system. This is a consequence of the fact that the Hamiltonian is even in the psi variable. Being even, it is invariant under the symmetry that keeps eta fixed and change the sign to psi. And this means that we can consider a time reversible equation. And also, which is an independent symmetry, it is even in space. So this means that the space of function even in x in the space, both eta and psi, is an invariant subspace for the dynamic of the system. And so we can look for solutions that are standing wave in this subspace of function, which is given by this symmetry. Both eta and psi are even in the space, and regarding time, eta is even in time and psi is odd in time. We look for small amplitude solutions, so the first thing to do is look at what happens at 0, linearize at 0. And we see that the linearized system looks this star system, eta t equal g of 0h of psi, and psi t is minus eta. G of 0 is the Dirichlet-Neumann of the flat strip. So it is simply d hyperbolic tangent of hd, where d means 1 over I dx, as usual in spectral notation. And the solution are this. You see, it is a a series, a Fourier series, where the spatial mod j is multiplied by oscillation in time with frequency omega j, which is given by the usual linear frequency relation, square root of j hyperbolic tangent of aj. We look for a quasi-periodic solution, and in this case it is a phenomenon already present at the linear level. The linearized operator at 0 already exhibits this kind of solution, which are described in this way. You see, the solution is the sum of cosine of omega jt cosine of jx. So each space Fourier mode evolves periodically in time with that frequency. If any two frequencies among those have an irrational ratio, take the square root of 2, for example, or something like that, so the function is not time periodic, but it is called quasi-periodic because it is the superposition of periodic motion, each one with its period. And so this is the notion of a quasi-periodic solution, and it is called usually almost periodic, and there are infinitely many. Non-zero amplitude with corresponding frequency that give irrational ratios. So the definition is the following. The classical definition is the following: consider a vector of frequencies with mutually irrational ratios, and a function u of tx is said to be quasi-periodic in time with frequency vector omega if this u of tx is a capital U function of omega 1t, omega 2t, and so on, and x, and for some function capital U, which is 2 pi periodic in each of its arguments. I made this punctualization because both yesterday at Gerard Yoss' seminar and the day before, it was unclear. I discovered that quasi-periodic, the word quasi-periodic is used in different meaning. For someone, quasi-periodic means periodic in the sense of Floquet, so it's a periodic oscillation, but at each period it gains exponentially factor in front. But it is completely different. In this sense, quasi-periodic means nothing grow and nothing decay, just oscillating, but in a very disordered way because of irrationality of ratios. So just to be clear. So the linear equation at 0 already has this kind of solution. So the natural question is, and the full nonlinear system does the same or not? Also have a quasi-periodic solution, and which one? This is a very old question. It goes back to Poincaré and Kolmogorov, Arnold, and Moser regarding dynamical systems. And So for small amplitude, we can look at the nonlinearity as a perturbation. So the question can be rephrased as the question of persistence under perturbation of the quasi-periodic motion in a Hamiltonian or reversible system. Okay, and this is the object of the so-called CAM theory. KAM, but I say CAM, which is shorter. Okay, in water waves, we have these two aspects that makes CAM theory difficult. One is that the perturbation is very strong because the nonlinearity contains derivative of the same order as the linear part, and this makes it a fully nonlinear problem. And even if we take the system and begin to differentiate many times, it becomes no longer fully nonlinear, becomes quasi-linear, but it remains quasi-linear forever. So it is something intrinsic. And also the linear part has eigenvalue with sublinear growth, like a square root of integers. And this makes it difficult to apply the usual reducibility scheme, as we will see in the next slide. Okay, regarding the result, we begin with fixing any finite subset of a positive integer, and we call it tangential sides, which is the usual name in this field. And we consider the solution of the linearized system at 0 that are Fourier supported on that finite set, S plus. And we look for quasi-periodic solution of the full nonlinear system, say eta psi with some frequency vector omega tilde, which has to be determined. And we look for a small amplitude, so we expect to find solutions that are close to the eta 0 psi 0 solution of the linear system, with some frequency vector which is close, not the same, but close to the frequency of the linear equation. And we set the problem in the Sobolev space, which is the space of function with finite Sobolev norm S, defined in Fourier in the traditional way. The usual way is this series, defining the norm in both time and space. L, I will use this notation. L is the Fourier index for space, the new dimensional space, and phi is the corresponding variable, and J, which is integer, is the Fourier index for the space X. Then fix any interval with H1 positive, H1, H2, in which the depth parameter can vary, H. And the theorem is, this is a bit long because it is the true statement, not a simplified version. So for every choice of the tangential sides, integer, of any cardinality, there exists some Sobolev regularity, say S bar, and some smallness, epsilon 0, such that for every amplitude psi, I go back, psi, square root of psi is the amplitude of the unperturbed solution from which we bifurcate. Positive and smaller than epsilon 0, there exists a Cantor-like set, a set G, subset of H1, H2, of good values for the depth parameter, which has asymptotically full measure as xi goes to 0, which means if xi goes to 0, the Lebesgue measure of the set fill the entire interval, such that for every good value of the depth, the gravity water wave system, WW, has a time quasi-periodic solution, eta psi, with frequency vector omega tilde, which is of the form it is, you see, at the first order in amplitude, it is the same formula for the linear solution, except that the frequency is omega tilde, has shifted a bit, plus some correction, which is of higher order, R1, R2, that are omega tilde quasi-periodic, and they have Sobolev regularity, and they are smaller regarding size in that Sobolev norm. The frequency vector, omega tilde, is Diophantine, and it satisfies this convergence. It converges to the linear vector frequencies when the amplitude goes to 0, as it is expected. The solution stay in the space of even in X, even T, odd in T function, in the invariant space of given by reversibility. And in addition, the quasi-periodic are quasi-linear, linearly stable in the sense of Aragu spoke yesterday. It means at a spectral level, the linearized operator at the solution has all purely imaginary eigenvalues. And the solution are defined for all time, and this is it has an additional interest because the Cauchy problem for this equation has not been proved to be globally well posed or ill posed. So it is an open question what the solution do evolving in time, and these quasi-periodic solution in time are special solutions that are example of globally defined solution. And since they are quasi-periodic, they don't exhibit any growth of Sobolev norm, but they stay forever in the same range. A first comment about the depth value. The theorem selects special values that are many, but not all, special values of the depth. And this could sound a bit strange, but if we rescale in a suitable way space, time, and amplitude, we can rearrange the statement to say that instead of keeping the wavelength fixed, we can consider the depth as fixed, and then the result becomes for many wavelengths we find quasi-periodic solution. Which in some sense, for me, it is more natural to think because depth is something that you see and wavelength is something that the system arrange. And okay, another comment about the linear frequencies. They have the asymptotic expansion as j goes to infinity. They are square root of j as if the depth were infinite, plus a correction which is exponentially small in j and uniformly in h, as long as h runs in a compact interval. And this is in some sense surprising because the parameter h moves the frequency only of exponentially small quantities, which could seem too little amount to recover all the nonlinear conditions that are required by Kamm theory, but instead it works, because we will see in a bit why, because even if this movement is exponentially small, we have analytic dependence. Hyperbolic tangent is analytic function, and even if it is the square root, that's not a big point. And because of analyticity, we can use non-resonance condition very mild using degenerate Kamm theory, which is a generalization of what Gérard Rios said yesterday. He used a transversality condition of the second order instead of the first. And analyticity can make it possible to use some more general transversality condition of some order. We don't know which one, but it is because of rigidity of analytic function. Okay, this is a very short list of relating paper because they are strictly related on standing water wave problem with small divisor, and so the list is very short, and it begins with Plotnikov and Tolan work of 2001 about time-periodic, pure gravity, and finite depth, and then other generalization by Jos Plotnikov and Toland in the successive years, and then more recent result by Al-Azhar and me, and Berti and Montalto, that prove the first quasi-periodic result in this field. And the result that I'm presenting now is the quasi-periodic version of Plotnikov and Tolan work of 2001. So it is time quasi-periodic with pure gravity and finite depth. So all this work have a small divisor problem, and all use a Nash-Moser iteration to deal with the nonlinear, to the construction of the solution, which said in very few words is based on Newton scheme and smoothing operator that are just Fourier truncations. And this is the general strategy to construct the solution. Say that the problem is f of u equals 0, just to fix a simple notation. All this problem encounter and solve one of the main points in the Nash-Moser approach, maybe the main point, which is the construction of a right inverse of the linearized operator, say f prime of u, at a point u which is not 0. And the point u, as long as the iteration goes, will converge to the true solution. Well, it is Newton's scheme, essentially. So even if it can be reformulated in other way. So when the nonlinear problem has a fully nonlinear or quasi-linear structure, then you see on the linearized problem, on the linearized operator, you see variable coefficient also at the higher order, in the higher order terms. And this is the what makes a quasi-linear problem especially difficult in the Nash-Moser application. And from the point of view of the small divisors, this inversion problem is more difficult in the quasi-periodic case. We have a more complicated small divisor structure, and in particular in the quasi-periodic case, it is more difficult for pure gravity when the eigenvalues are square root of integer than for capillarity. So the general strategy is to find transformation, changes of variable that conjugates the linear operator to another one in which we can invert. So let's speak about reducibility problem first. By an abstract result of Berti and Ball, we can restrict the analysis of the invertibility on the complementary of the tangential sides that are called normal sides, denoted by SC, complementary. And reducibility problem is quite simple to explain. Is this: assume we have a linear operator L0 of this form, omega the phi plus a diagonal term d plus some small remainder r of phi, which is variable coefficient. And assume that we are writing everything in a Fourier basis, so they are infinite dimension matrices, both D, which is diagonal matrix, and R, and D has purely imaginary eigenvalues. In the periodic case, we can invert by Neumann series in this way. The constant coefficient part has eigenvalues omega dot L plus some lambda j, which in general accumulate to 0. But if we are able to impose the so-called first Melnikov non-resonance conditions, that are this inequality you see here, and we try to invert, we have to prove that the remainder R is relatively bounded with respect to the linear part. And in the periodic case, this is possible if R is sufficiently regularizing in space. And this is possible because in the periodic case, the pair of the pair Lj of Fourier indices in time and space, where there are small divisors, are connected, are along a line. So if you control J, you control also L. If you control space, you control also time around the manifold, the curve of small divisors. And this is the point why in periodic case Neumann series give invertibility as soon as you impose just first Markov condition. This is not true in the quasi-periodic case, and it is very easy, the reason. The reason is that instead of, you have omega here, you have omega dot L, but omega dot L does not control L. Omega dot L in dimension more than 1 can be small or some order 1, even if L is very big. It depends on the rotation with respect to the vector omega. This is the difference. And so this method doesn't work. And so we look for another classical approach, which is Kamm reducibility scheme, which says this. Take L0, the operator above, and try to conjugate it to a similar one, same form, where D plus is diagonal, and R plus is the new remainder, which is quadratically smaller than before. This in some norm you use in the scheme. So write the transformation phi as identity plus some correction psi to be found, and plug in the conjugation equation L0 phi equal phi L plus, the new one, and let's see what at the first level, at the linear level of psi, you find. You find the so-called homological equation, which is this equation for the correction psi, and read in Fourier. In Fourier, it is this boxed equation. You see that the eigenvalue, the small divisor now are slightly different than before. Not slightly, are different from before. It is omega dot L plus some lambda j minus lambda k. So you have to control the differences between two eigenvalues. Lambda j are the eigenvalues of D. There is the difference because when you commute matrices, you find differences of eigenvalues. So when L is 0 and j is equal to k, the factor is 0, and so you cannot remove it, and you take it. But if L is 0 and j is k, this gives a correction to the diagonal part. So we are happy, it is diagonal piece. The point is what to do with all the other Ljk, and we have to put it at the denominator, and they are small, so we have small denominator, and we impose some quantitative version of saying that this is non-zero denominator, which is the last inequality I wrote, and they are called second Melnikov condition. The scheme works because we have this small denominator, we control it, it produces some big factor in front. It is that L to tau here, which is in a Fourier psi is like to say that when you construct psi from R, you are paying tau derivative in time. There is a loss of derivative, but so you make the usual trick, which is truncate and see you have the loss of derivative becomes a factor, a big factor because of truncation, becomes a big factor in front of your formula, but you have this quadratic scheme, and you know the Newton scheme or any quadratic scheme can converge even if there is a diverging factor in front, because it is quadratic, provided you start from a very sufficiently small guessing point at the beginning. And this is essentially the CAM reducibility scheme explained in 2 slides. However, in the gravity wave, this cannot be done because eigenvalues are like square root, but there is hyperbolic tangent, but is not the point here in what I'm saying now. And we cannot impose the standard second Melnikov condition. You see, the differences between two in square root of j minus square root of k, where j and k are integers, is a dense set. So we have no hope to impose some bound for omega L plus square root of j minus square root of k, which is independent of j and k, simply because being dense, it accumulates to 0, whatever is omega, whatever is L. And so we impose weaker than usual second Melnikov condition, which means take into account the fact that it goes to 0 with L, not only with L, but also with J and K. So it is this J and K here at the denominator. And okay, what's the effect of this novelty in the second Melnikov condition? The effect is double, I would say, because on some point we have J. Okay, there is J and K. Suppose J is on the left and K is on the right. J is the row index of the matrix and K is the column index. K to D is the Fourier representation of a derivative acting on the argument of the operator. It's like dx. The J to D is like some dx at the beginning. So when you have a derivative applied to some coefficient and the argument, the derivative distributes in a usual way. Some derivative affect the coefficient, some derivative affect the argument. And so you have also consume irregularity on the coefficient. And so the effect in the end is both consuming the regularity of R because of J minus K and increasing the order of R because of K to D. As a pseudo-differential operator, we have increasing the order. So we compensate the loss of regularity in X truncating, just to dealing with loss in X as we do with, and everyone do, loss in time. This is unusual, but it is in some sense very natural. We have a loss, truncate, and control what the increasing coefficient make. And to compensate the increasing order, instead, we have so we have R to be sufficiently regularizing to produce a zero order final operator. So say that R is regularizing of order M. So in the end, we get psi of order 0. And since psi is order 0, the remainder at the next step remain of the same order minus M as before. And so the circle is closed and the iteration can be done. This is one step. You do infinitely many steps, and in the end you have the complete diagonalization of this vector. So, okay, in 5 minutes I will do the remaining 15 slides. And okay, so we have to make CAM reducibility with this new weak second Melnikov conditions. We have to verify, to do 2 things. One is to verify that for many parameters such weak Melnikov conditions are satisfied. Otherwise the result is empty. And the other one is to find transformation that conjugates the linearized water wave operator, which is quite far from being omega de phi diagonal and regularizing. The opposite is not that way. we have to conjugate to this form, to an operator of this form with the regularizing term, with variable coefficient is regularizing, at which the CAM reducibility scheme can start. So regarding the first point, the parameter satisfying the Melnikov condition, we have consider a full torsion curve, which means a curve which is not degenerate, well, which is not contained in any hyperplane, and consider the linear frequencies, square root of j hyperbolic tangent of hj. We denote it by little or capital omega according to the fact that j is tangential or normal size, but the formula is exactly the same. We use the analyticity of the function, and in fact, since there is the square root, we use the analyticity of the same function with h to power 4 instead of h, so it removes the singularity given by the square root. And we use also a generalized van der Monde determinant result, quite recent, which is 2000. And we prove that the curve of frequency vector, any combination of this frequency vector, are full torsion. So they never belong to a hyperplane. They are never flat. They continue to curve in the space. We use analyticity again, which gives a analyticity says that if something is not flat, then some coefficient must be non-zero in the Taylor expansion. And so we use and we deduce this transversality property, which means sum of the first k0 derivative of this expression that correspond to 0 first, second with plus, and second with minus Melnikov non-resonance conditions for the unperturbed frequencies. Okay, sum of the first k0 star derivative is big. And this condition, this transversality property is stable under perturbation. So these are in a state, don't me pressure, 1 minute more. Just 1 minute. Just one. They are stable under perturbation, so the perturbed eigenvalue also satisfy this. And just one word to say transversality. Transversality says that either our function is big, and so the value of h is already good, we have no small divisor, or if it is small, then we have a small denominator, small quantity in the denominator, so that h can be erased from the good set, but we control derivative in some way. If we have first derivative, it means that it leaves quickly the set where the divisor is small. If the derivative is not the first, but the second or third or the 1,000th, it is the same. We have worst estimate, but in any case, we are able to control the measure of the bad set. And in the end, we use a theorem by Russman on the measure of the level set of function controlling derivative to deduce, well, which is nothing very strange, it is just a calculation. We deduced that the bad value of set has a very small measure. And so there is a lot of other. Finished. Okay.
Maybe. Okay, Gerard.
Okay. As far as I remember 10 years ago, in the infinite depth case, the infinite dimensional kernel gave something always periodic in time and x. Which is not the case here because of the finite depth. But when you fix the number, a priori you fix the number of modes you want to consider, then normally the amplitude, the square root of xij, should satisfy some very strict relationship between them. In the infinite depth case, this is 1 over n square or something like that. But in your case, is it the case, or you cannot choose arbitrarily this square root of phi j? Amplitudes.
The amplitude are, in this case you mean, or the
Yes, in your case.
yes, it is, no, okay, some value you have to exceed. Let's go back.
Yeah, yes. The before.
No, okay, here is written for every amplitude small.
Every phi j?
Okay, here is every amplitude, but
So you can choose any set of finite.
you can also use amplitude.
Because we have time.
Okay.
The answer is very simple. For finite depth, it is a very good analytical formula, and everything is independent. It has nothing to do with infinite dimension. I'm sorry, it is the time for the next talk. We can discuss later. Thank you.